Slide 1. Peripheral circulation is a series of slide tape programs developed and produced by the American Physiological Society. This is Hemodynamics. Content expert, Dr. Chien, Professor of Physiology, Columbia University, College of Physicians and Surgeons. 2. The study of peripheral circulation encompasses the hemodynamics of blood flow, the properties of the arterial and venous systems, the exchange of materials between blood and tissues, and the mechanisms and systems that control the systemic circulatory function. 3. In this program, we consider the basic principles of blood and fluid movement, including the relationships among pressure, flow, and resistance in blood vessels. These principles will be discussed in detail following a few general introductory comments. 4. As you know, during systolic contraction in a cardiac cycle, blood is ejected from the left ventricle into the arterial system, and during diastolic relaxation, the aortic valve is closed and the left ventricle refills with blood. The contractile force of the heart raises the pressure within the left ventricle and the arterial system, providing the driving force that causes the forward motion of blood. The arterial pressure falls during diastole, reaching its lowest point just prior to the next ventricular ejection. For a detailed description of cardiac structure and the mechanics by which the heart muscles generate force, refer to the APS slide tape series, Cardiac Physiology. 5. The mean arterial pressure during a cardiac cycle is shown here as 90 millimeters mercury. In normal young adults, the mean arterial pressure ranges from 80 to 100 millimeters mercury. 6. The blood pressure in the systemic circulation is highest in the large arteries that receive the blood pumped out by the left ventricle. The pressure in successive segments of the vascular tree decreases progressively, reaching its lowest level in the great veins returning blood to the heart. The progressive pressure decrease reflects dissipation of energy. It is related to two major factors: the flow properties of the blood and the geometry of the vascular network along the path of flow. 7. The flow characteristics of the blood arise from the fact that it is a suspension of cells in plasma. Its inhomogeneous composition results in complicated flow properties and affects the manner in which energy is dissipated in association with the movement of the cells and plasma through the vasculature. 8. The size, number, and structure of vessels in successive vascular generations determine their roles in the dissipation of pressure and control of blood flow. The architecture of the arterial vasculature involves progressive branching from several large elastic arteries down to a large number of small muscular arteries. 9. The terminal vessels of the microcirculation consist of the arterioles, the capillaries, and the venules. In the broadest terms, the arterioles are the vessels responsible for flow control and are a major contributor to the dissipation of pressure. The capillaries are responsible for exchange of materials between blood and tissue, and the venules act as collecting vessels. 10. On the venous side of the circulation, the venules coalesce into small veins that continue to combine, eventually forming the large conduit veins. Because the venous system acts as a volume reservoir, it plays an important role in the distribution of blood volume. 11. In summary, the blood pressure in the systemic circulation is highest in the large arteries that receive the blood from the heart. The pressure decreases progressively along the path of flow, reaching its lowest level in the large veins that return the blood to the heart. The pressure loss is related to the flow properties of blood and the nature of the vascular network. 12. Your first objective is to be able to describe the relationship between pressure and flow and to define the factors that determine the resistance to flow through the vessels. 13. The pressure drop in the circulatory system is analogous to the pressure drop in a system of tubes connected to a circulating pump. The fluid in the tube receiving the pump output has the highest pressure, and the pressure drops progressively along the path of fluid flow, reaching the lowest level in the part of the tube returning to the pump. This system can be used to illustrate the hydrodynamic principles that underlie circulatory hemodynamics. 14. The mechanical function of the pump imparts energy to the fluid in the tube receiving the output, and thereby raises the pressure. The fluid flows from this region of high pressure toward regions of lower pressure further from the pump output. In this system, the fluid is assumed to be a simple fluid, such as water, and the flow is steady. 15. At low velocities, the flow of fluid is streamlined, and the path of each fluid element is parallel to the direction of flow. The rate of fluid flow, Q, has the units of volume per time. As the fluid flows from one region to another, energy is dissipated due to internal friction in the fluid. This is manifested as a drop in pressure. The total pressure drop in this section is symbolized as P1 minus P2. Usually, units of millimeters mercury are used in blood circulation. 16. The measure of the difficulty encountered in pushing a fluid through a system of tubes is resistance, which is defined as the ratio of the pressure drop to the volumetric flow. Resistance tends to retard flow and causes the drop in pressure. 17. The equation for resistance can be rearranged to indicate that the pressure drop at a given volumetric flow rate varies directly with the resistance, and that the volumetric flow rate for a given pressure drop varies inversely with the resistance. 18. In streamlined flow of a simple fluid through a rigid tube, the relationship between pressure drop and flow rate is linear. At a given pressure difference, the higher the resistance to flow, the lower is the flow rate. The factors contributing to resistance and the mechanisms of energy dissipation are the subjects of the following discussion. 19. In streamlined flow through a cylindrical tube, the motion of the fluid can be visualized as a series of concentric annular layers. Hence, this is also referred to as laminar flow. In reality, each annular layer is infinitely thin. In this simplified model, each shaded area represents the average behavior of a large number of such thin layers. 20. For a simple fluid, there is a parabolic velocity profile across the tube. Because of frictional retardation by the wall, the fluid immediately adjacent to the wall is stationary, and the layers of fluid successively closer to the center of the stream move with progressively greater velocities, reaching a maximum velocity in the center of the tube. With a parabolic velocity profile, the mean linear velocity of the fluid is equal to 1/2 of the peak velocity in the center of the tube. 21. During laminar flow, the internal friction between annular layers dissipates pressure energy in the form of heat. The physical property of a fluid that causes internal friction is the viscosity of the fluid, eta. The unit of measurement of viscosity is poise. 1 poise is 1 gram per centimeter second. In laminar flow, the viscous resistance factor, RV, varies directly with the viscosity of the fluid. 22. For a given pressure difference, the volumetric flow rate is lower for a fluid with high viscosity than for a fluid with low viscosity. 23. Viscous resistance also varies directly with the length of the tube. For a given flow rate, fluid viscosity, and tube radius, the longer the tube, the greater are the resistance and pressure drop. 24. The next few slides demonstrate the strong dependency of volumetric flow rate on the radius of a tube. The volumetric flow rate through a tube in centimeters cubed per second is equal to the product of the tube cross-sectional area in centimeters squared and the mean velocity in centimeters per second. Notice first that the cross-sectional area of the tube is equal to pi times the square of the radius. If the radius were doubled, the cross-sectional area would increase to 4 times its initial value. 25. Notice also that the mean velocity of a fluid flowing with a parabolic profile varies directly with the square of the radius. Therefore, doubling the radius increases the mean velocity to 4 times its initial value. 26. Both the cross-sectional area and the mean velocity vary with the square of the radius. Since the volumetric flow rate is equal to the cross-sectional area times the mean velocity, the volumetric flow rate varies directly with the radius raised to the 4th power. Doubling the radius would increase the volumetric flow rate to 16 times its initial value. The influence of radius can also be expressed in terms of resistance to flow. In combination with the other factors contributing to resistance, we see that resistance varies directly with blood viscosity and tube length, and inversely with radius raised to the 4th power. 27. In summary, the pressure drop during laminar flow is proportional to the product of the volumetric flow and the viscous resistance factors, which are fluid viscosity, tube length, and tube radius raised to the 4th power. Therefore, the volumetric flow rate can be expressed as proportional to the product of the pressure drop and the reciprocal of the resistance factors. The proportionality constant for this relationship is pi over 8. In this form, the equation is referred to as Poiseuille's law or the Poiseuille-Hagen law. 28. Write the equations that give the relations among pressure drop, flow, and resistance. Give 3 equations to show how each of these parameters is related to the other 2. Write the equation for volumetric flow by using the Poiseuille law and express the resistance in terms of its component factors. Please stop the tape while you answer these questions and those that follow throughout the program. 29. Resistance is defined as the ratio of pressure drop to volumetric flow. The pressure drop equals volumetric flow times the resistance, and volumetric flow equals the ratio of pressure drop to resistance. Poiseuille's law states that volumetric flow is equal to the product of the pressure drop, the ratio of the 4th power of the radius to the product of fluid viscosity and tube length, and the constant pi over 8. The resistance term would be written as 8 times the viscosity and tube length divided by pi times the radius to the 4th power. 30. Your next objective is to be able to discuss the resistance factors during turbulent flow and to give a means of estimating the likelihood of turbulence. 31. A variety of factors affect the onset of turbulent flow and contribute to flow resistance during turbulent flow. The next few slides show the development of turbulent flow due to increasing flow velocity. Here, during streamlined flow through a tube with uniform diameter, the flow rate is low, and deviations in the paths of fluid elements from streamlines are so slight that only the viscous resistance factors affect the pressure-flow relation. 32. As the flow rate increases, the fluid particles gain momentum. This magnifies any deviation from straight streamlines and results in an instability of motion. Instead of slipping past one another, as in pure viscous flow, the fluid particles interact with one another due to their momentum. As the flow pattern becomes less orderly, there is a transition from laminar flow to turbulent flow. 33. Under these conditions, fluid elements may move sideways or even opposite to the main direction of flow, and eddies may form. Consequently, more energy is dissipated in the increased complexity of this disordered motion. The resulting drop in pressure is referred to as the turbulent pressure drop. 34. The ratio of the turbulent pressure drop to the flow rate is referred to as turbulent resistance, RT. During turbulent flow, the total resistance is the sum of the viscous resistance and turbulent resistance. When the flow rate increases, turbulent resistance and turbulent pressure drop become increasingly important. 35. At very high rates of flow, the flow pattern becomes so disordered that flow is completely turbulent. Viscous resistance becomes insignificant in comparison to turbulent resistance, and the entire pressure drop is attributable to turbulence. 36. The onset of turbulence and the turbulent resistance vary directly with two factors in addition to flow velocity. Since turbulent pressure loss is related to the momentum of the fluid, turbulent resistance is directly related to fluid density, rho. The denser a fluid, the more readily disorderly flow develops. And since disorderly flow develops more easily in an open space, an increase in tube diameter, d, tends to increase the likelihood of turbulence. In summary, increases in density, velocity, and/or tube diameter tend to increase the likelihood of turbulent flow and increase turbulent resistance. 37. On the other hand, viscous resistance is directly related to fluid viscosity, which has a damping effect on disorderly flow. Therefore, the likelihood of turbulence decreases with increases in fluid viscosity. 38. The Reynolds number is a commonly used parameter for estimating the likelihood of turbulent flow. It is defined as the product of fluid density, mean velocity, and tube diameter divided by the fluid viscosity. The three factors in the numerator are those that tend to promote turbulence, whereas the fluid viscosity in the denominator is responsible for viscous resistance and is the factor that opposes turbulence. Consideration of the units of measurement of the various factors indicates that the Reynolds number is dimensionless. 39. At very low Reynolds numbers, flow is laminar. If the Reynolds number is raised above a critical value, turbulence occurs. The critical Reynolds number is approximately 2,000 for flow in a straight tube. The higher the Reynolds number above the critical level, the stronger is the degree of turbulence. The critical Reynolds number may be considerably lower than 2,000 when the tube geometry is not uniform. 40. The shape of the curve relating volumetric flow rate to pressure difference varies with the onset of turbulence. At low flow rates, when the Reynolds number is below the critical limit, turbulent resistance is insignificant, and the relatively constant viscous resistance in laminar flow results in an essentially constant slope. When flow exceeds the critical limit, turbulence begins. The addition of turbulent resistance to viscous resistance raises the total resistance, causing the flow rate to fall below that predicted on the basis of a linear pressure-flow relationship. 41. Write the Reynolds number formulation. State the units of measurement for each factor. Define the critical Reynolds number. 42. The Reynolds number is dimensionless. It is the ratio of the product of fluid density in grams per centimeter cubed, mean linear velocity in centimeters per second, and tube diameter in centimeters to the viscosity of the fluid in poids or grams per centimeter second. The critical Reynolds number is the Reynolds number at which turbulent flow begins. 43. Your next objective is to be able to describe the determinants of blood viscosity. 44. In the circulatory system, the total resistance to flow is the sum of the viscous resistance and turbulent resistance. Under normal conditions, turbulent resistance is generally negligible. So, in most parts of the circulation, the viscous resistance factors dominate the relationship between flow rate and pressure drop. 45. Although Poiseuille's law cannot be quantitatively applied to the circulatory system, the general principles are valid. That is, the viscous resistance to blood flow varies directly with blood viscosity and vessel length, and inversely with the vessel radius raised to some power that is probably close to 4. The inhomogeneity of blood and complexity of the vascular system make it difficult to quantitate the exact contributions of these factors to circulatory resistance. 46. Since blood is a suspension of blood cells in plasma, its flow properties are much more complicated than those of a simple fluid. The volume of red blood cells expressed as a percentage of the total volume of blood is defined as the hematocrit and is a major factor determining blood viscosity. The red blood cells normally occupy approximately 40 to 45% of the volume of blood. That is, the hematocrit is 40 to 45%. The white blood cells and platelets account for less than 1%. The hematocrit may vary with the physiological state, and it may change significantly in pathological conditions. 47. Normal blood plasma has a viscosity of approximately 1.2 centipoise, Cp, at 37 degrees centigrade, which is 1.7 times the viscosity of water. With the presence of 40% red blood cells, the viscosity of blood under normal flow conditions is approximately 2.8 centipoise, or 4 times the viscosity of water. A variety of factors affect the viscosity of whole blood. 48. The relationship between hematocrit and blood viscosity is nonlinear. The effect of the hematocrit on viscosity is greater at increasing hematocrit levels. For example, when the hematocrit becomes 70%, the blood viscosity may be nearly 3 times that found at a normal hematocrit level of 40%. 49. The concentration of cells in the blood is not the sole determinant of the blood viscosity. Blood viscosity is also a function of the deformability of the cells. The normal red blood cells deform easily in response to the hydrodynamic forces in the circulatory system. The deformation of the normal red blood cells and the alignment of the cells with the direction of blood flow serve to keep the blood viscosity at low levels. If the red blood cells were rigid particles, blood viscosity would be nearly 5 times higher than that found normally. 50. In a number of blood disorders, the deformability of red blood cells is reduced. For example, in sickle cell anemia, gelation of the sickle hemoglobin rigidifies red cells following deoxygenation in the microcirculation. This results in the formation of cells with sickle or other bizarre shapes and an increased blood viscosity. 51. Plasma proteins, such as fibrinogen and some of the globulin fractions, can bridge the surfaces of adjacent red blood cells to form aggregates known as rouleaux, if there are insufficient hydrodynamic forces to cause disaggregation. low flow rates and the presence of abnormal amounts of certain plasma proteins may favor red blood cell aggregation and cause an increase in blood viscosity. 52. In vitro measurements show that blood viscosity increases sharply as near zero flow is approached. This is mainly because there are insufficient hydrodynamic forces to prevent red blood cell aggregation. In addition, there are insufficient hydrodynamic forces to deform the red blood cells, so they behave essentially as rigid particles, causing increases in viscosity. In most parts of the circulatory system, the normal flow conditions are such that there are sufficient hydrodynamic forces to prevent cell aggregation and to induce cell deformation, keeping the blood viscosity near the low plateau shown for high flow velocities. 53. Finally, for very narrow vessels, the viscosity of blood may be dependent on vessel radius. For vessel radii less than 300 microns, Faraeus and Lindqvist found a progressive decrease in viscosity value. Several explanations have been proposed for this effect. 54. Determination of the hematocrit value indicates that it is progressively reduced in small-size vessels, and this low hematocrit can account for some of the reduction of blood viscosity. 55. Although normal red blood cells have a radius of approximately 4 microns, they can undergo deformation to traverse narrower vessels. The deformed red blood cell is relatively close to the vessel wall, with only a very thin plasma film in between. As a result, viscous resistance increases in vessels less than 3 microns in radius. When the tube radius is smaller than 1.4 microns, the red blood cell cannot deform sufficiently to effect passage, and the viscous resistance becomes extremely large. 56. We have discussed 5 factors that affect blood viscosity. List them and explain the effects of slow flow rate on blood viscosity. 57. Blood viscosity is affected by the plasma viscosity, hematocrit, red cell deformability, red cell aggregation, and vessel radius. In low flow states, there is a decrease in the hydrodynamic forces available to disaggregate and to deform the red blood cells. As a result, blood viscosity increases. 58. Your next objective is to be able to discuss the effects of vessel geometry on viscous resistance to blood flow. 59. We have been discussing the determinants of blood viscosity, a major factor in viscous resistance to blood flow. You should realize that under physiological conditions, blood viscosity is maintained at a relatively low level. And as you will see in the next program, physiological control of flow resistance is achieved mainly by regulating the geometry of the resistance vessels. Since the length of vessels does not change significantly once an individual is fully grown, vessel length can be considered a fixed factor in flow resistance. However, by virtue of the fourth power relationship, vessel radius has a powerful effect on flow resistance. Changes in the radius of the resistance vessels are the most important physiological mechanism for the dynamic control of resistance to flow. 60. For example, the fourth power relationship indicates that if the radius of an arteriole is constricted from 200 to 100 microns, the flow resistance in the constricted state is raised 16-fold. 61. The strong dependence of flow resistance on vessel radius is graphically shown on this slide. Constriction of vessels leads to a marked increase in resistance. 62. As the vessel radius decreases, the resistance increases and flow is reduced. 63. The influence of vessel radius on resistance and flow may also be seen in the following situation. Since vessel walls exhibit passive elastic behavior, which will be discussed in detail in a later program, an increase in intravascular pressure may lead to distension of the vessel. 64. For a vessel exhibiting passive elastic behavior, the increase in radius in response to distending pressure is accompanied by a decrease in resistance and an increase in flow. Vasodilation can also be induced by actions of neurohumoral agents on the vascular smooth muscle cells, which is discussed in later programs in this series. 65. If the vessel radius has been doubled due to vasodilation, what would be the resulting change in resistance and volumetric flow rate? 66. The resistance in the dilated state would be 1/16 of the original resistance, and the flow would increase 16-fold if the pressure drop remains constant. 67. Your last objective is to be able to describe the role of turbulence in the circulatory system. 68. As we have said, the total pressure drop during flow in the circulatory system is due predominantly to viscous resistance. However, because of the complexities of the vascular geometry and the pulsatile nature of blood flow, one needs to consider the contribution of turbulent resistance in some parts of the circulatory system. Remember that the Reynolds number is an index of the relative contribution of turbulent resistance versus viscous resistance and may be used to estimate the likelihood of turbulence. 69. For example, the density of blood is approximately 1.06 grams per centimeter cubed, and blood viscosity is approximately 0.03 poise, or grams per centimeter second. At the root of the aorta, the mean linear velocity may reach 100 centimeters per second or higher during systole, and the diameter is approximately 2 centimeters. Therefore, the Reynolds number may reach 7,000 in the root of the aorta during systole, far in excess of the critical level. Some turbulence has also been observed in the aorta. 70. Laminar flow is silent, whereas turbulent flow may be audible. This is important in interpreting sounds in the cardiovascular system. For example, the turbulence just outside the heart valves contributes to the generation of heart sounds. Murmurs are generated by fairly regular eddies. 71. In an artery with a diameter of 0.6 centimeters and a systolic linear velocity of 25 centimeters per second, the Reynolds number is approximately 500. Since turbulence tends to set in at low Reynolds numbers in the presence of complex vessel geometry, turbulent resistance may become significant at branch points. 72. A localized narrowing with a distal dilation is prone to generate turbulence and sounds in the dilated region. This is one of the reasons why sounds can be heard over the brachial artery in the antecubital fossa when the artery in the upper arm is partially constricted by inflation of cuff pressure to levels between the systolic and diastolic pressures. 73. In severe anemia, the reduction in blood viscosity and the increase in blood flow velocity raise the Reynolds number and favor the onset of turbulence and murmur. 74. In a small artery with a diameter of 1 millimeter and a linear velocity of 7 centimeters per second, the Reynolds number is only about 25. Blood flow is laminar and viscous resistance factors dominate. 75. The Reynolds number decreases markedly in the microcirculation. In a capillary with a diameter of 10 microns, 0.001 centimeters, and a mean linear velocity of 0.1 centimeters per second, the Reynolds number is only about 0.004. Therefore, flow is never turbulent in these small vessels. 76. In a medium-sized artery, the mean linear velocity is 10 centimeters per second and the diameter is 1.5 centimeters. If the blood viscosity is 3.18 centipoise and the blood density is taken as 1.06 grams per centimeter cubed, calculate the Reynolds number. 77. The Reynolds number is approximately 500. Since this is near the critical Reynolds number, eddies and turbulence may begin to occur at the branch point or bend. 78. For the same artery with a diameter of 1.5 centimeters, if due to severe anemia the blood viscosity is reduced to 1.56 centipoise, the blood density decreases to 1.04 grams per centimeter cubed, and the mean linear velocity increases to 20 centimeters per second, calculate the Reynolds number. Discuss the likelihood of turbulence in this vessel. 79. The Reynolds number is 2,000. This is approximately equal to the critical Reynolds number for a straight tube. Considering the more complicated geometry of the circulatory system, the critical Reynolds number should be much lower than 2,000. Therefore, there is a good possibility for turbulence to occur in this artery in severe anemia. 80. This concludes the presentation of hemodynamics. To assess your understanding of the concepts discussed and for a list of additional readings, please refer to the study guide that accompanies this program. This program was developed and produced by the American Physiological Society. Copyright 1980.